Hello, Superstar Algebra 1 students. We're back with our actual last lesson of Topic 6. And if you remember, Topic 6 was all about quadratics in vertex form. Focusing on that really quickly, and you're going to want to write this at the top of your paper, we learned that quadratic equations are equations that have a square in it. Now, there is more to that, and we will focus on that for the next couple units as well. But our general equation that we practiced for this unit was a times x minus h squared plus k. And we called this HK form or vertex form. Now, there's actually three types of HK form equations we've learned so far, and you don't need to write these other two. I just wanted to show you the differences because I have a bunch of students that always ask me, wait, how do we know what shape the graph makes? And that's a really, really good question. So at this point in time, you should be comfortable with these three types of equations. And notice that they all have the same letters in them, y, a, x, h, and k. But they all make three different shaped graphs. Our first equation at the top just has parentheses, and if you were to distribute A and simplify, you would get a typical linear equation. That's what we studied last semester, that linear equation that has x and y, and so we say that this is linear. And hopefully you remember that linear equations make some sort of diagonal line. The only thing different about the second equation is that instead of parentheses, we have these bars running up and down here, and hopefully you remember these bars are called absolute value bars, and they cause a quantity inside to become positive. Now, this equation is known as a linear absolute value equation because we're just doing absolute value of a linear part. And we learned that linear absolute value functions, and that was a pretty terrible graph, make a V-shaped graph. You can remember value V, right? It's even in the word. And then last but not least, this almost looks like a linear function. We're back to parentheses again, but now we have a square. And we learned before that in the word quadratic, we have the Latin prefix quadra, which you sometimes hear in Spanish too, right? Quadra. You use that with like a block or a square as well. So that's where the square comes in, and quadratics make U-shaped graphs. So we do need to be able to recognize the type of graph based off of one of those three equations. Right? Those are the majority of the graphs that we see this year. There's one other type that you'll learn at the very end of this semester, but those are the three big ones. So let's go ahead and actually get to the lesson. Lesson 6.5 is about key components. Components are like parts. Key components of parabolas. So what we're going to try and do is we're going to put together the first two lessons where we learned how to graph basic parabolas. And then these last two lessons where we learned how to solve quadratic equations. And we're going to put all that together to try to graph really nice parabolas and identify everything important about those parabolas. So strangely today you're not really learning any new math. You're just putting all the math together that you hopefully already know. And if you're a little shaky on it, you get to practice a little more. So let's begin. Parabolas are the graphs of quadratic equations, right? Quadratic just means that the largest power in the equation is a square. As an opener, we'd like you please to graph this equation that's down below. F of x equals x minus 3 squared minus 4. And some of my students looked at this and they said, oh, that f of x thing, that always throws me off. What does that mean we do? Well, don't let it scare you. F of x is just the function notation way to write the output of an equation. So if you don't like that f of x and you'd rather replace f of x with a more common variable like y equals x minus 3 squared minus 4, that's totally okay, right? It's just a different way to write it. It's not using function notation. It'll still be the same graph. Now, if you've forgotten how to graph, you can always look back to your first couple videos or notes. However, the key thing we need to remember is that A, which is that invisible one hiding, H, and K are the three things that will help us graph our parabola. So please go ahead and pause this video, try to use A, H, and K to graph the parabola, and then once you've tried, unpause, and we'll see how you did. Ready, set, go. All right, you're back. Well, to graph a parabola, the first thing we need to do is find its vertex, right? That kind of bottom piece right here. We need to figure out where the parabola begins. And hopefully remember that the vertex for a parabola is related to the h and k in our hk form, where we have our h that's up here and our k that's over here. Except the weird thing with HK form is no matter what type of equation, linear, absolute value, or quadratic, we always do the opposite of what H looks like. So H looks like -3, that means it's +3. And then K is easy, K is just whatever's at the end, including the sign, so it looks like -4, it is -4. That's enough to help us graph the vertex, right 3 and then down 4, right? We're just graphing this point on our coordinate plane. And that's awesome. We have 1 point. But we should be able to graph at least 3 points at this point in time. So how do we graph the rest of the points? Oh, I think we can use our a value as long as we write that a value over 1. And that tells us we can go up 1 over 1 in each direction to get 3 points. Now don't keep going up 1 over 1, because if you do that, that's going to make your V-shaped graph, and we're trying to make a parabola here, a U-shaped. But up to this point, all we've said is once you have 3 points, and maybe your teacher showed you how to find more, which is great, but once you have 3 points, we've generally said, okay, now just make a U. And that's great. So you go through and you make that U-shaped graph. Awesome. Or maybe when you make your U-shaped graph, your U goes a lot wider. Or maybe you're one of those where you make your U-shaped graph and it kind of curls straight up. And up to this point, we really haven't cared how you've made that U-shaped graph. It's totally up to you. What we're going to do today is learn how to make a better U-shaped graph. Maybe learn a quick way to find more points and use those key components to perfect these awesome parabolas. As we do that, we're going to learn some new vocabulary, just like in Part B right here. Part B says, where is the axis or line of symmetry? Well, we actually learned this with absolute value, and you know what line of symmetry is. You learned that actually in art way long time ago, where a line of symmetry is where you crease or you fold your paper, and a shape folds on top of itself on the other side. Well, and I bet you could probably even see if you were to crease your paper along this dashed line that I just drew here, that the right half of the parabola would fold on top of the left half. This line is known as an axis of symmetry. AOS is a very common abbreviation for axis of symmetry. Now, how do we explain to someone what this line is? Because we don't just want to say, oh, it's that dashed line, I'm pointing at the paper, but you can't see me, so how do you know where I'm pointing? Well, we can write the equation of the line of the axis of symmetry. We spent all last semester practicing lines, and this is one of those special cases where we set up above in HK form, if you have both x and y, it makes a diagonal line. But if you have a vertical line like this or a horizontal line, that's going to be an equation that either only has x or only has y. And one easy way to determine which one it is to realize that this line passes through the x-axis. And so that's a pretty good giveaway that the equation for our line is going to be x equals what? Well, we pass through an x value of 3. Now, is there a faster way we could have done that without even graphing? Because a lot of today is going to be great. You had a graph and that helped you, but could you have done it without a graph? Well, I think the component of the parabola that decides where this line is going to be is the x-coordinate of the vertex. And how do we find the x-coordinate of the vertex? Oh yeah, it's just h. So for x equals 3, we're just going to say that it is the h value in the equation. That's a very fast way to find the line of symmetry. Just find the h value, say, oh, line of symmetry, x equals 3. Awesome. All right, Part C. Part C throws 5 words or phrases at you that really, for our intents and purposes, all mean the same thing. Now, we're only going to talk about 2 of them in depth today, and we're going to discuss the other 3 later on. The 3 we're going to discuss later on are roots, answers, and solutions. So if you're talking about an equation and they say, I want you to find the roots, or I want you to find the solutions to this equation, then really what they mean is they are looking for the zeros. but what are zeros? Oh, zeros are actually just a fancy way to say the x-intercepts. Now, I have an acronym that I use ZIRAS, Z-I-R-A-S, and that just comes from the first letter in each word. Oops, and I circled the X over here, awkward. Z-I-R-A-S. And that's just to help remind you that all of those mean the same thing. Zeros are just the x-intercepts. We're probably most familiar with the word x-intercept, so let's do that for part C. We want you, for this parabola over here, to identify where the x-intercepts are. But there might be an issue there because my parabola doesn't even go up to the x-axis, right? This is our x-axis up here, and x-intercepts are where the graph crosses the x-axis. So how do we do that? Well, for now, let's just, however you drew your U-shaped parabola, just go ahead and bring it up to the x-axis. It doesn't matter where. We just want you to make a quick guess. So for mine, and I'm not saying if it's right or wrong, it doesn't matter, mine seems to cross the x-axis at these 2 points. These 2 points? That's so vague. Let's be specific. What 2 points does my graph cross the x-axis, or where are the zeros of my function? Well, we should hopefully remember that to write a point on the x-axis, we moved along the x. There's going to be an x value. Mine looks like maybe it's like 1.5 or so, but it didn't go up at all. It's stuck on the x-axis, so it's 1.5, comma 0. Now, when I did this in class with students, some students said it was 1, comma 0. One student said it was negative 3, comma 0. Their parabola is really wide, and it doesn't matter as long as the second value here is 0. My other one looks like it's about 4.5, comma 0. You do need to notice, though, that for x-intercepts, the y value is always 0. All right, what about the y-intercept? Well, the y-intercept is very similar, except now we want to see where our blue parabola crosses the y-axis, and that could be pretty tricky depending on how steep your parabola is or isn't. I'm going to kind of draw mine out here, and it looks like, I don't know, maybe it crosses it like 6 or so. Mine kind of wanted a weird little curve here, so maybe it's higher than 6, and you can just guesstimate it. It's not a big deal. So if I wanted to write the coordinates, I wouldn't just write 6. That's not a point, right? Where is 6 on my graph? Is it over here? Is it where the 2 6's meet? We need 2 points, an x and a y. This point up here has a y of 6, but an x of 0. And so for y-intercepts, we say the component for the coordinate is 0, for the x coordinate is 0, and the y component is 6. Great. Let's dive a little bit deeper into these zeros, or I'm going to call them real zeros. There is a such thing as imaginary zeros. You won't deal with that until Algebra 2, so no worries there at all. So let's maybe ignore the word real, and we're going to think, how many zeros, aka x-intercepts, can a parabola have? So I think you're probably going to want to draw maybe 3 coordinate planes down here. They don't have to be perfect, right? Mine aren't even going to have tick marks on it. I'm just literally drawing 3 of these. And based on the opener that we did up above, we saw that, and I'm just going to redraw that down here, we saw that my opener had 2 zeros. Okay? The y-intercept does not count as a 0, so it has 2 zeros. Or couldn't my parabola have been like way up here and gone down if you wanted? So this actually shows 2 parabolas here, but each of those parabolas has 2 zeros. Your goal, and I'm going to ask you to pause me, is to draw a few other parabolas, and our parabolas, at least this year, either have to be pointing up or down. They can't go sideways, and they can't be like squiggly. They have to be U-shaped, either up or down. Your goal is to draw a few other parabolas that have a different number of zeros. So these ones had 2 zeros each. Can you draw a parabola over here that has a different number of zeros? 3 zeros, 1 zero, 0 zeros? So go ahead and pause me and we'll see what you come up with. You're back. Well, if you want a hint, and I'm going to have you try one more time, one of your parabolas that you're going to draw is only going to have 1 0. And then the last parabola that you're going to draw is going to have 0 zeros. So can you picture a parabola that only crosses the x-axis once? Can you picture a parabola that crosses the x-axis 0 times? Pause me again and try. Ready, set, go. All right, hopefully you did something like this. The 1, 0 is always tricky. There's a couple ways you could do it, but I find most people bounce it off the x-axis like this, and they put the vertex on the x-axis. Or you could have drawn this the other way. You could have had it moving in a downwards direction, but still the vertex, I think, has to be on the x-axis somehow. 0, 0s I find students do really well with. They go, oh, to cross 0 times, it just has to be floating. Well, it can't be floating down below, because parabolas go on forever. They have to. But what if it's floating up above? That, I think, will never cross the x-axis, and same thing if you wanted to see it pointing in a downwards direction. Neither of those will have any zeros. I'll circle these just to make it clear. All right, well, that's all fun and exciting, but could we maybe predict the number of zeros of a parabola without graphing? Well, thinking about the opener up at the top, right, could we have looked at this equation and said, well, based on what I know about A, H, and K, hence you'll want to look at A, H, and K, could I know that that already crossed the x-axis 2 times? Or maybe another way to phrase this is, what makes a parabola cross the x-axis twice? Where does it have to be located? Which way does it have to be facing? So why don't you go ahead and think about this? I did give a few hints to this as well, and then we'll come back together and see how you did. Ready, steady, go. Well, hopefully you decided that there are 2 important pieces that determine the number of zeros of a parabola. The first thing you're going to need to do is you're going to need to identify, and it doesn't have to be written exactly like this. Hopefully you already wrote a way to do this. You're going to have to identify the location of the vertex, right? And that just means looking at H and K. And in fact, if you're really good at this, you might realize that you only need to look at K. H actually doesn't affect if our graph is going to have the number of zeros our graph will have. Once you've figured out where the vertex is, let's say the vertex is like up here, you might be tempted to say, oh, that's a parabola that has no zeros because it won't cross the x-axis. But what if the parabola went in a downward direction? Now it has 2 zeros. So what's the other thing we need to look at once we've determined the location of the vertex? Well, the second thing we need to look at is use the value of A. Because A controls, right, if A is greater than 0, if A is positive, your parabola goes up. But if A is negative, your parabola goes down. And by combining those 2 facts, you can really visualize how many zeros there are without even having to graph, right? I could have looked at this equation and said, this is 3, -4. So visualizing in my head, I might go 3, -4 is down in that 4th quadrant. And then A is positive, so I know it's opening up. That means right away, I know there are 2 zeros. Last part of this first page, how many x-intercepts, or how many zeros, or how many solutions can a quadratic equation have? Well, the most, so we'll say x-intercepts, if we're talking real zeros for our intents and purposes again, you could either have 0 zeros, it doesn't cross the x-axis, 1 of them, or it can cross twice. However, y-intercepts is a little different. Okay? Can you picture a parabola that crosses the y-axis twice? I don't think so. I think if the parabola went out and then crossed again, it'd go back on itself. It wouldn't make that U shape anymore. And then these 2 points line up in a vertical line, which means this wouldn't even be a function. And this year, we only study functions. So I think it is impossible for a parabola to cross more than once. Can a parabola cross 0 times on the y-axis? What about this guy right here, right? Some students will say, ooh, well, this one just goes up and up and up, and it never gets to the y-axis. Well, actually, parabolas go up and out forever. So it's not a V, it's a U-shaped, and they might go out at a very, very slow rate. But eventually, this parabola will get wide enough that it spans everything you can think of from left to right. So it must cross the y-axis. So for our x-intercepts, there could be 3 possibilities. There's 0 of them, 1 of them, 2 of them. For our y-intercept, though, we'll do it like this. There can only be 1. That's it. Now, we've gone over a lot of the theory on this page, and hopefully this was pretty helpful in terms of how parabolas work. This second page is saying, okay, cool. We were able to talk about all this, but how do we actually find them, right? You made me guess at the x-intercepts and guess at the y-intercepts on this equation. Can we find the actual x and y-intercepts? Well, yes. In fact, this is one of our main themes of Algebra 1. If you get out of Algebra 1 knowing how to find x and y-intercepts, your Algebra 2 teachers are going to be so happy. There's some other things you should know how to do, like solve an equation, but finding x and y-intercepts is huge. And it's the same process every time. In fact, this is probably the third time this year that you've seen this. So let's remind you. All zeros, so x-intercepts, are located, shockingly, on the x-axis. If you have a point on the x-axis, then your point is going to be some x value, you move left or right, comma 0. If y is 0, then you stay on the x-axis. If it's not 0, you're off the x-axis. If you have an equation, then, and you wanted to find the zeros, you wanted to find the x-intercepts, then because this point has a y of 0, then we look in our equation and we replace y with 0. Once y is gone, then we just have to use SADMAP to solve for x, to isolate x. Once we've isolated x, we'll have found the 0 or the zeros, if there's more than one, of our graph. Easy. The y-intercepts are almost exactly the same. The y-intercept, all y-intercepts are located on the y-axis. Again, very shocking. That means there has to be a y value in the point, but the x value will always be 0. If you have an equation then and you wanted to find the y-intercept, you make the x go away by replacing it with 0. And then you use SADMAP and try to isolate y. Right? It's just the same as the x-intercepts. So let's look at a practice problem here. Determine the vertex, zeros, and y-intercept from the vertex form of a quadratic equation. Well, the vertex is pretty easy, I think, right? So the vertex we've done before. We need to, and it says how do you find it? We need to look at h and k in the equation. All right, well, where are h and k? Let's color code this. We'll do h in blue. We'll do k in green. Looks like h is over here and k is at the end, right? HK form. We know, of course, that we do the opposite of h, comma, whatever k is. You might even recognize this equation. Isn't this what we did on the opener? Is this vertex a minimum or maximum? Well, what I always like to do is just sketch a really quick graph. I'm not going to put really anything on here in terms of tick marks. 3, -4, the vertex is somewhere down here, fourth quadrant. And then we have to see, is my parabola going to open up or is my parabola going to open down? Well, based on the fact that a is +1, that means my parabola opens up. If your parabola opens up, then we say that the vertex is a minimum. This vertex is the smallest point on our parabola. So when they say what's the location and what's the value, usually it's defined that the location is the x coordinate of the vertex. So it is located at an x value of 3. And the value of the minimum, the smallest value that's on the graph, is a y value of -4. So it's really just a different way to look at the vertex. Now if our parabola had been upside down, this would have been a maximum value. It's the largest value there. All right, let's try our next one. How do we find the zeros? Well, we look at our equation and we look at our cute little organizer up above, and it says finding the zeros. So we should probably follow these steps. It says replace y with 0. So you look at this and go, ugh, I don't even see the letter y in the equation. But the step is replace y with 0. So we should probably do that. To do that, let's rewrite the equation, and instead of f of x, let's go ahead and replace f of x with y. We did that on the opener, didn't we? So we have y equals, I'm not going to write the 1, no reason to make things more complicated. Y equals this, and we're going to replace y with 0. Now that we've set 0 equal to y, or 0 equal to the whole equation, our goal is to figure out what is the value of x. Well, doesn't this look like what we did last class in lesson 6.4? I think our goal is just to isolate x here, and we know how to do that. We just did a whole bunch of practice problems last class, and it is all about SADMAP. So I'm going to remind you of the order over on the side, and then we're going to go ahead and get this guy solved. So 0 equals x minus 3 squared minus 4. If we solve, we need to undo addition and subtraction first, although you might want to undo subtracting 3. It's locked inside by that exponent, so we need to undo the subtracting of 4. All right, that now leaves us with 4 equals x minus 3 squared. We're done with our addition and subtraction, at least that was on the outside that we could get to. The next thing we look for is multiplication and division, but there's only two things attached to x. There's a minus 3, and then there's a square that's trapping everything inside. So no multiplication division at all. We're down to the exponent, and that is something we can undo. So we're going to go through, take the square root. We learned last class that the square root undoes or cancels a square. The square root of 4 is 2. Once we've undone the square, there's nothing holding these parentheses up. They fall down at this point, and we're here. Now, we're going to go ahead and solve this equation. So I'm going to quickly rewrite it one more time just for some space. And I think to solve, if we want to isolate x, there's only one number that's acting on x. It's being subtracted by 3, so we can add 3 to both sides. And that gives us that 5 equals x. Or another way to put that is we found x is 5 when y is 0. Now the nice part about this is we can actually check our work here because this is the problem that we warmed up on today. So let's go back to the first page and let's make sure that it makes sense that 5, 0 could be where my parabola crosses the x-axis. So we just found the point 5, 0. I guessed 4.5, but I think 5 makes sense, doesn't it? So if we wanted to go through and check that, we're just going to continue up on this side. That looks pretty good. That looks pretty U-shaped to me. But do you see the issue? We found a 0, an x-intercept of 5, 0. But how many zeros are there here? We're below the x-axis and going up. There should be another 0. So looking back on the second page, how come we only found 1 0? And hopefully you caught my mistake because it was a mistake and it was on purpose. We learned last class that whenever you write in or introduce a square root, you need to consider both answers. There are two answers to the square root of 4. Positive 2 times positive 2 is 4, but negative 2 times negative 2 is also 4. So to solve this, we actually create two equations. One equation with the positive 2 as the answer, but the other equation with negative 2 as our answer. Then we can go through and solve. To solve here, we still add 3 to both sides, but be careful. Don't think that just because one of them was 5, the other answer will be negative 5. Negative 2 plus 3, or 3 minus 2, is 1. And so our other 0 is an x of 1 when y is 0. Two answers to a square root. You got to be careful there. Now if I go back to that previous page, let's make sure that 1 makes sense. So I got an answer of 1 over here for my 0, and I think that does make sense, right? I think we can go through and say, oh, that's 1. Let's go ahead and connect those points. So it looks something like this. There we go. That does make sense. It's right in the spot or close to the spot that we expected it to be. Some of you might even have guessed 1 and 5 over here, right? And nice job. All right, so we have a parabola here. This parabola actually has 5 points, which is very exciting. I think we're almost done with this. Not quite, but almost done with it. But we still need to find the y-intercept. The y-intercept is essentially the opposite of the x-intercept. If on the x-intercept we replaced y with 0, then for the y-intercept we are going to replace x with 0. And I'll keep the equation in terms of y equals here just so it looks all right. So we have y equals, parentheses, 0 minus 3 squared minus 4. Now this is kind of a weird situation because to find the x-intercept, x was not isolated on one side of the equal sign, so we had to use SADMAP to isolate it. But on this second one, y is isolated, y is by itself on the left. So then we know the answer. The y-intercept is 0 minus 3 squared minus 4. Well, that is a number, but it's an unsimplified number. So we don't need to isolate y here. What we need to do is simplify the other side. And when we simplify, we work the other way, really. We work forwards through PEMDAS. So y is already by itself. Let's go ahead and do what was in the parentheses up here. So 0 minus 3 is negative 3. Took care of the parentheses. Then we do what the exponent asks us to do. Negative 3 times itself. Negative 3 times itself is 9. There's no multiplication or division left, so we just have to do the addition and subtraction, and 9 minus 4 is 5. So what did we find here? We found that when x was 5, the y value, or when x was 0, the y value became 5. We found that the y-intercept is 0, 5. And now we can actually do even more to our parabola back on the first page. We know that the y-intercept is the point 0, 5. And that's going to help us find an even better U-shaped graph. It's going to look something like this, and then up here. But wait, there's actually even more. This line of symmetry is so useful here. Notice what happens when we find a point on one side. When I found this point over here, this point was 1 away from the axis of symmetry. So I could go 1 away on the other side, and oh, there's a point. I could have even done that with my x-intercept up above. This point is 2 away, so there has to be an x-intercept that's 2 away over here. Or looking at the y-intercept is 3 away. So couldn't I go 1, 2, 3 away to the other side and find another point? Using the symmetry of a parabola to help you plot points is a great time saver, because if you find a point like the y-intercept on one side, then you'll automatically know where the point is on the other side just by using that line of symmetry. And so we can even increase the accuracy of our parabola by including another point. Alrighty, now we just took a long time to do one problem, and not all the problems are that long, I promise. So let's go ahead and try another one. This one you guys should do on your own. It's very, very similar to the one we just did up above. So we're going to see how you do, and then once you are done, unpause and you can check your work. Ready, set, go. All right, you're back, so let's work through all of this. We can see that a is negative 1. Our h looks like it's positive 2, so we have to do the opposite and make it negative 2. And then our k is 25. Our vertex then is going to be opposite of h, comma k. There's my vertex. Is this vertex a minimum or a maximum? Again, I just sketch a really quick graph. It doesn't have to be perfect. Negative 2 and up 25 is somewhere up here. How do we know which way the graph is going, though? We look at that a value. As a is negative, a is less than 0, my parabola is going to be going down. All right, well, what did we say about that vertex then? We say the vertex is a maximum. It is the highest point on this parabola. The vertex is located at x equals negative 2 and has a value of y equals 25. Next up, we need to find those zeros, and we practiced this before. To find the zeros, that's like finding the x, so we want there to still be an x in the equation, which means we need to set the y, or the output, equal to 0. 0 equals negative 1 times x plus 2 squared plus 25. To solve, it's our usual SADMAP. We're trying to isolate a variable, so we work backwards through PEMDAS. Can't do anything in the parentheses. The square is locking it in. And we're not going to undo the square until we go through PEMDAS. So we'll start with our addition and subtraction here. Looks like we could subtract 25 from each side. That gives us negative 25 equals negative 1, which is multiplying times x plus 2 squared. We took care of addition and subtraction. Now we're on to multiplication and division, and I do see a -1 that's multiplying here. The more you practice these, the faster you're going to get at seeing the answers. Negative divided by a negative is a positive. Any number divided by 1 is that number itself. We still can't get into the parentheses. There's still a square locking them in, but we finished multiplication and division, which brings us to exponents. We can undo our exponent with a square root, but this time we won't trick you. Whenever you write in a square root, you need to include a plus minus. And so, and I'm running a bit out of room, I'll have to use the bottom of the paper here, we find the square root of 25. What times itself is 25? That one's not bad, it's just 5. Is equal to x plus 2. Don't forget the plus minus. From here, 2 equations to solve. One equation will give us positive 5 equal to x plus 2, and the other equation will give us negative 5 equal to x plus 2. Solving the equation on the left, hopefully we can see we need to subtract 2 from each side, and that will give us that x equals 3. And on the other side, we also subtract 2, but be very careful. If one answer is 3, do not expect the other one to be -3. -5 minus 2 is -7. And so we find 2 zeros here. We find the 0, 3, 0, and the second 0, -7, 0. 2 x-intercepts exactly as we expected over here. Last but not least, we need to find the single y-intercept. I'll switch the g of x to y for clarity here so it makes a little bit more sense to you. Y equals -1 times, we want the y, we're trying to find the y-intercept, so we don't want an x. X is going to become 0 here. And yippee, y is already isolated, but then that means we need to go through PEMDAS and simplify the answer on the right side. PEMDAS says do what's in the parentheses first, and we can do 0 plus 2. Easy enough. Next up, we took care of that. Do the exponent. 2 squared is 4. Do any multiplication and division. We do have a -1 times 4, which is -4. And then do any addition and subtraction. You can treat this as -4 plus 25, but it might make more sense if we do 25 minus 4. And so our y-intercept was found by evaluating our equation when x was 0, and we found that y was 21. Now it does look like a bunch of work, but there aren't that many steps, right? Here we had 3 steps and then 1 easy equation to solve, and then this right side is just simplifying, something you've been doing for a couple of years now. So it looks like a lot, but the more you do this, the faster you're going to be, and you're just going to be flying through this in no time. So we have some more practice for you. There are 2 equations. Your goal is to do the same thing that we've been doing. You want to find the zeros, which is a fancy way, of course, to say the zeros, the intercepts, the x-intercepts, that is. R stands for roots, A for answers, S for solutions, and we'll cover those more later on. You have to list the vertex, the axis of symmetry, and find the y-intercept. We've covered all of this so far, so you definitely want to try this without me, and then if you get stuck, we can come back together. Ready, set, go. All right, we're back. Let's go ahead and find those zeros first. Doesn't matter what order we go in. The zeros are the x-intercepts, so we need to set the y, or the output, to 0. -x squared plus 9. Now we need to isolate x. I see a few things happening to x. -1 is multiplying, the 2 is squaring, the 9 is adding. And I think we can do this without writing SADMAP this time, right? We just need to undo addition and subtraction first. So that's going to give me -9 equals -1 times x squared. Undo multiplication and division next. So we have 9 equals x squared. And then there's only one thing left that's attached to x, that is a square, so let's undo it with a square root. Don't forget that plus minus. And because there's just one thing here, let's do our quick conclusion. X is going to be both positive and -3. So I think that probably gives us 2 answers here. It gives us the x-intercept 3, 0, and the x-intercept -3, 0. 2 x-intercepts, as we'd probably expect. The vertex is actually a little tricky for this one, I think. Vertex-wise, it's pretty tough to see this in HK form, but I think we can do it. With HK form, the negative is going to be outside. X is always in the parentheses, and the square is always outside the parentheses. There's no parentheses with the 9, so that has to go at the end. Then we can fill in those extra missing numbers. -1 is our a value, and since nothing is adding or subtracting to x on the inside, we could just put a plus or a minus 0. Can you see the vertex now? Our vertex, h0, you could say, is it -0? Sure, same as 0, comma 9, right? Our h and our k. What's our axis of symmetry? Well, we learned earlier that the axis of symmetry goes through the x-axis. It goes through the h value of the vertex. So just x equals 0. And last but not least, the y-intercept. This one's not bad at all. We'll change f of x to be y, and we replace the x with 0. Well, 0 squared is 0, -0 is still 0, and it looks like our y-intercept is 9, or it's the point when x is 0, y is 9. Okay, let's go ahead and get all this graphed and make sure all of these points make sense. We'll know if it makes sense when you go to connect them, if we can create a nice U-shaped graph that goes through all of these. Okay, so the y-intercept is easy. That's 0, 9. We have an x-intercept of 3, 0, and -3, 0. And although 3 points are fine, we usually like to have 5 or so points for a parabola. How can we create more points here? Well, don't forget that from the vertex, we can use the a value to go 1 point in each direction, down 1, over 1. So I'm going to take this vertex up here, 0, 9, and you might notice that the vertex is actually the same as the y-intercept. That happens sometimes. We're going to go down 1, over 1 in each direction. And now we have 5 points. So let's finish the parabola, sketching in, bringing our artistic abilities into play, and get that U-shaped graph. All right, now you saw me do one. Why don't you guys tackle this last one? Ready, set. Oh, and by the way, you're going to want to write kind of small for the x-intercepts. I think there are a bunch of numbers there. It's going to take a few steps. Go. All right, we're back again. Let's give this a shot. Hopefully by now you're comfortable with those x-intercepts, setting your y equal to 0. And again, I'm going to write pretty small here. Sorry about this in advance. And let's do this in black so we can show the colors for each step. So 0 equals 1/2 times x minus 2 squared plus 2. And actually, maybe in order to save some room, I'm just going to tell you the step, and I'm not going to show you what I'm doing to each side. Yeah, let's do that. So the first step is to undo adding 2. So we subtract 2 from both sides. 0 minus 2, well, that gets us some alternate colors. That gets us -2. Then we have to undo this multiplication here. And I will show this step because it can be tricky. This is a fraction. To undo multiplying by a fraction, we actually multiply by a fraction. And so the easiest way to do that is to multiply by the reciprocal, which in this case is 2/1. But 2/1 is really just 2. So what we're doing is we're multiplying both sides by 2. The reciprocals undo each other. 2 times -2 is -4. And then we end up with x minus 2 squared on the other side. What comes next? Well, we're still moving through SADMAP. We need to undo that square. To undo the square, a square root, of course. Plus minus. Those undo. And then we end up with x minus 2 on the right side. But what about the left side? The square root of -4. Is that going to be plus minus 2? We should probably check that. Is 2 times itself equal to -4? Well, no, 2 times 2 is equal to +4. So maybe it's the negative one. Is -2 times -2 equal to +4? No, negative times a negative is also equal to a positive. So what is this answer? Oh, we might remember from last class or the class before, the square root of a negative number in Algebra 1 does not exist, right? It's not a real number. And so as soon as we get it does not exist, we actually get to stop. Now, what does that mean about the x-intercepts? Well, if there are no answers, then we would probably say something along the lines of, there are no x-intercepts. That seems kind of weird, so we'll look at this graph later on and maybe we'll understand why there are no x-intercepts. Let's finish the rest of this. The vertex goes pretty fast, right? Opposite of h, comma k. The axis of symmetry is just the h value. And the y-intercept, well, there's a little bit of math here, but it's nothing terrible. We are just going to replace our x with 0 and evaluate the right side using ZADMAP. Nope, using PEMDAS. There it is. So PEMDAS, do the inside of the parentheses first. Then the exponent, negative 2 squared is 4. Then the multiplication, half of 4 is 2. And last but not least, any addition or subtraction. So we found a y-intercept of 4. All right, let's see what this looks like graphically and try to understand why there are no x-intercepts here. So they're telling us that the vertex starts at the point 2, comma 2. All right, I can buy that. And then let's see, what else can we do with this? Well, we know the y-intercept. The y-intercept is 0, comma 4. That's up here. We know the axis of symmetry. The axis of symmetry is what our graph is going to fold over on. And so if this point is 2 to the left of the axis of symmetry, then couldn't we put a point 2 to the right over here, mirroring that point over the line of symmetry? And that's looking pretty good. But those 5 points, how do we get other points here? Well, don't forget we can use this a value. Now, this a value gets a little tricky. We might remember that if we're going to use an a value to find a point for a parabola, we need to write the a value over 1. So this tells us go up 1/2, to the right or to the left 1. So I'm going to go ahead from the vertex. I'm going to go up 1/2, and then to the right 1, or up 1/2 and to the left 1. And this gives us our 5 points that we can very nicely artistically turn into our U-shaped graph. You'll notice this parabola is less steep than a normal parabola because the slope is half as large as normal, right? So we'd say that this graph is either wider or compressed or less steep. Any of those work. And then looking at this, can we understand why there are no x-intercepts here? Well, the graph never goes down to the x-axis. It starts above the x-axis and then goes up from there. So it should make sense that there are no x-intercepts. Alrighty, we really know everything we need to do to be successful for today, so we just have a bit of practice here, and we'll do the same thing. You guys will try the couple problems, then you'll unpause, see how you did, and then we'll do the same thing on the back. So ready, set, go. Alright, let's rock and roll. Vertex, opposite of h, comma k, -1, comma -2. Let's do all the vertices first. This vertex, opposite of h, -1, comma that invisible k, 0. Opposite of h, comma k. Vertices, check. Axis of symmetry, super easy. It is just the h coordinate of the vertex. X equals -1, x equals -1, x equals 2. Alright, the number of real zeros. I always have to sketch just a little bit of a graph. It doesn't have to be much. You can really even kind of sketch it just right here. I mean, nice and small on your paper, nothing bad. The vertex, -1, -2 is in the third quadrant. And then the a value, that's the real killer here. This a value is negative, which means our parabola opens down. How many zeros or how many times does this cross the x-axis? 0 times. There are no real zeros here. All right, our second one, I bet I can even just sketch a nice little graph using this piece right here. The vertex is -1, comma 0. That's on the axis. My a value is 1, so my graph has its vertex on the x-axis and goes up. I only see one real zero there. Last but not least, we'll use this one more time. Our vertex is 2, -4, that's the fourth quadrant. And our a value is 1, so our graph opens up. I see 2 zeros here. right? Just by showing that nice little graph, just super, super small, we can get a really good indication of what's happening. They did ask us to find the y-intercept here. This is the only part where you're going to have to write kind of small, but I think we'll be okay. The y-intercept is found by replacing x with 0. And I think especially if we start working some mental math, it's not bad at all. 0 plus 1 is 1, and 1 squared is still 1. Working to the right, negative 1 times 1 is negative 1, minus 2 more gives us a y-intercept of negative 3. Or if we wanted to write it as a point, x was 0, y was negative 3. We'll do the rest of these as well. So my y-intercept is found by replacing x with 0. There was a plus 0 at the end. I'm not even going to work that though. 0 plus 1 is 1. 1 squared is 1. So our y-intercept, not a lot of work this time, is 0, 1. Last but not least, we have x replaced with 0. And we're just going to start simplifying. 0 minus 2 is negative 2. Negative 2 squared is positive 4, and 4 minus 4 is 0. So this y-intercept is kind of a weird one. It's the point 0, 0. The y-intercept is the origin. Last part, domain and range. Well, the domain is really easy. The domain for every equation that we do all year long, at least in this Algebra 1 class, will be all real numbers. There are any number of ways to explain this. We can say that you're allowed to put any x value you want into this equation. You might be asking, what? Why would we not be allowed to? Well, that's maybe a story for a different day. Another way to think about it is that the domain also measures how wide the graph gets. And these U-shaped graphs get infinitely wide. They keep getting wider and wider. It may not look like it because don't they go straight up? They don't go straight up and down. They get wider and wider. But long story short, every domain of every graph we do this year will be all real numbers. There's a bunch of ways to write all real numbers. You can write it the way I did here. You could write this in our interval notation, negative infinity to infinity. It's telling us that x can be any number in there. Or you could even get really fancy and you could say x is an element. It's a part. That's like a curvy E. Then we do a double bar r. And that r means x is a part of the real numbers, or x can be any number of all the real numbers. All of these work. They all get full credit, whatever sounds good to you, as long as you're telling us that x can be any number. The range, though, how do we do that range? That's something we haven't covered yet in this class. But if the domain measures how wide the graph goes, maybe we can think of the range as measuring how tall our graph gets. Well, looking at our graph over here, how tall does that get? Well, it looks like the highest it gets is the y value, or the k value of our hk. And our k value is negative 2. So the highest my graph gets is to negative 2. And then doesn't it go down forever from there? I think so. So our range, talking about how tall and short the graph gets, we could say this in a couple ways. One way is you could say the y values are less than or equal to negative 2. Negative 2 is the tallest it gets, and it can be smaller than that. Or you could say something along the lines of, if negative 2 is the highest and it goes down forever, doesn't it go down to, let's say, negative infinity? And so the other way we can write that in interval notation, if you want, is we go from negative infinity to negative 2. We use that square bracket on the right side because we can be equal to negative 2, and we always use parentheses with infinity because you can never actually be equal to infinity. Infinity is not a number. It just means really, really negative in this case. All right, let's look at these other two because they go a little faster. Range here, well, the lowest the graph gets is 0. That's our k value from our vertex, and then it goes up from there. So one way you could write this, the y's are greater than or equal to 0. The other way to write this is you can say we start at 0 and we get larger than that. Let's try one more. The last one, we have this graph again over here. We need to look at the k value of our vertex. K is negative 4, which means the lowest our graph ever gets is negative 4, and it goes above that. So our range, the y values are greater than or equal to negative 4. Or we could say we start at negative 4 and we go up away to infinity. Okay. So there are a bunch of shortcuts we just talked about here, and we're going to give you a quick minute to write all of those down. What should you mention? Well, you should explain how we found the axis of symmetry. You should explain how we found the range. Both h and k are very useful. You should also explain the shortcut of sketching a little graph to see how many zeros there are. So take a very quick second or two or a minute or two, jot down how we did these problems while they're still fresh in your mind. The more that you can write this down in your own words, the more you're going to understand. And then we'll move on to the last page. Ready, set, go. All right. We're on to that last page. This last page just has a couple questions, and that's nothing really different than what we've been doing before. Your goal is to graph the parabola using 5 points, and you're going to have to fill in these two parts first, the vertex, zeros, and y-intercept. So, ready, set, go. All right, you're back. We're going to do this one the fastest we've done so far. -3, -9, opposite of h. Zeros. 0 equals x plus 3 squared minus 9. Add 9 to each side. Square root each side. Don't forget the plus minus. Make two equations. I'll do it something like this. One equation, 3 is equal to x plus 3. The other equation, -3 equals x plus 3. Subtract 3 from each side here. Also do that on the other equation. And so we end up 3 minus 3 is 0, getting x equals 0. And we also end up with -3 minus 3, which is -6. So I see two zeros here, or two x-intercepts. When y was 0, x was 0. And when y was 0, x was -6. Nice. Y-intercept? Well, we have y equals 0 plus 3 squared minus 9. Whoops. As we continue this out, 0 plus 3 is 3, 3 squared, 9 minus 9 is 0. So when x was 0, y was 0. You might notice that the y-intercept was the same as one of the x's. And when we put this on here, it's going to make a lot of sense. So, vertex first, -3, -9. -3, -9. Look at that. It fits perfectly on the graph, almost like we meant that to happen. Y-intercept, 0, 0. X-intercepts, -6, 0, and 0, 0. They're in the same spot, and that does happen sometimes. I only see 3 points. They asked for 5. How can we create 5? Oh, right. Don't forget our a value is up 1 over 1. So up 1 over 1, up 1 over 1. And now we have our beautiful parabola like so. Oof, that one's in trouble. That's a little better. And there we go. Let's do the last one. Vertex. Oh, there's an invisible plus 0 there. Sneaky, sneaky. Our vertex looks like, oops, we'll do it like this. Opposite of h is 2, 0. Let's find the zeros. So we set 0 equal to negative, I'll put the invisible 1 that's there, x minus 2 squared. We can't get to the minus 2, so we have to undo the -1 that's multiplying first. Okay, so we get 0 equals x minus 2 squared. And then we should probably square root. Plus minus. But it's kind of weird to say plus minus 0. I mean, you're right. 1 is positive 0, 1's negative 0, but that's the same 0. So we usually leave that off if we just get 0. And so to finish this off, we add 2 to each side. And it looks to me like we're getting x equals 2. Now you might be saying, wait, shouldn't there be 2 x-intercepts here? Well, let's just run with it for a second. X was 2 and y was 0. Let's see if that could be the answer, or if it's not, I bet we'll be able to see what the other one is pretty quickly. Okay. Y-intercept. So y equals negative 0 minus 2 squared, negative 2 squared. Exponent comes first. Negative 2 squared is 4. Negative times 4 is negative 4. So my y-intercept looks to be when x was 0, y was negative 4. Let's get this graphed. The vertex, 2, 0. The y-intercept, oh wait, the vertex is 2, 0, and the x-intercept is also 2, 0. That's weird. They're in the same spot, but that can happen. Y-intercept, 0, negative 4. Let's use the line of symmetry. If this is the vertex, then we can kind of see, and I'm going to erase this, that the shape of our parabola is going to look like this, but that's going to help us find one more point. We can see 2 to the left and also 2 to the right. But we wanted 5 points. Oh, right, the a value again. We're not going to keep forgetting that. Down 1 over 1, so let's get 2 more. Down 1 over 1 each direction, and there is our beautiful parabola. Nice. All right. I think we're going to go ahead and stop for here. If your teacher wants you to do the last question, they can take you through it. But we have done all the basics. Look at all this awesome math we did. We put everything together, and you guys are ready to start your review for your test. Thanks for hanging out with me. Hopefully this made a lot of sense. And if I did anything wrong or you need something else explained, just let me know. Bye, guys.